So now we're going to talk about direct and partial variation. So when we talk about direct variation, it occurs when the ratio of the variables does not change. Or in other words, when the dependent variable is a constant multiple of the independent variable. And we can algebraically show this or define it as y equals mx times x, or m is equal to y over x. The slope or constant of variation, which would be represented by m, is equal to the dependent divided by the independent. And the graph passes through the origin. So, a few examples here. Find the slope or constant of variation, which is our m value. The distance traveled by a car varies directly with time. The car travels 270 kilometers in 3 hours, while our dependent is y and our independent is our x. Using the equation m equals y over x, that's the same as writing 270 kilometers over 3 hours, right? Because our independent would be time and our dependent would be distance. When we take 270 divided by 3, we end up getting the unit rate of speed, which in this case is 90 kilometers per 1 hour. Well, we know that that is the constant of variation. So the slope or constant of variation is 90 per 1 hour, or 90. The total cost varies directly with the number of games bought. 8 games cost $480. Well, we have our equation. Our slope, or constant of variation, is equal to dependent over independent, which is cost over number of games. So we're trying to find the cost per 1 game, which in this case would be $60. So the constant of variation is $60 per game. If Chris works part-time at Licks and earns $7.50 per hour, describe the relationship between his pay and the hours he works. Well, for every hour he works, he earns $7.50. Write an equation for the relationship. What is the slope or constant of variation? Well, if we let P equal the pay and H be the number of hours, his pay is determined by his rate of $7.50 for every hour that he works. And if we look at it, this is the equation that we see. Y equals mx, y equals mx. We're just not using those variables. We're using it in the context that we understand from the information given to us. But this format is something that we're going to need to know a little bit later on. If he makes $78.75 in a week, how many hours did he work? So he made $78.75 and his rate of pay is $7.50 per hour. We need to know how many hours he worked, so we divide both sides by 750. We end up getting a value of 10.5. So therefore, he worked 10.5 hours in order to earn $78.75. A little bit more in-depth example here. We have a graph to go along with it to visually represent things. Carly is driving to Montreal at 60 kilometers an hour. So fill in the table of values to show her distance at 1 hour, 2 hour, all the way up to 10 hours. And then we're going to go ahead and graph. So for the hours, here's 1 hour all the way down to 10. And at 1 hour, we know that she traveled 60 kilometers because it's 60 kilometers per 1 hour. After every hour, she goes an additional 60 kilometers. So we can simply just kind of plot those values in, increasing by 60. On the graph of time and distance, I know at 1 hour, she drives 60 kilometers. At 2 hours, she drives 120. At 3 hours, she drives 180, and so on and so forth. So the relationship looks like this. Is it a linear or non-linear? Well, it's pretty linear. Where does it cross the y-axis? It crosses the y-axis right at 0 and 0, because at 0 time, she has traveled 0 distance. That's what that means. Write an equation to find the distance she traveled, d, after t hours. So the distance she traveled is dependent on 60 times the number of hours that she travels. Using the equation, determine how far she could travel in 15 hours. Well, our equation is d equals 60t. Our t is given to us now, it's 15. So 15 times 60 gives us a distance of 900 kilometers. So the relationship above is an example of direct variation. Or another way is the distance varies directly with time. Or y varies directly with x. When we talk about partial variation, a really good way to talk about it before we get into it is seeing an example. A large pizza costs $6. plus $2 per topping. So fill in the table of values to show the cost of a pizza with 0, 1, 2, all the way up to 5 toppings. And then we're going to graph it appropriately. So the number of toppings, 0, 1, 2, 3, 4, 5. We know that with 0 toppings, it costs $6. And then for 1 topping, it's an additional $2. So then I keep adding the number of toppings. It's increasing by $2 for each of those toppings, and I get my cost values or my Y values here. So at 0 toppings, at 0 number of toppings, it's $6. At 1 topping, it's 8. At 2 toppings, it's 10. At 3 toppings, it's 12. And we kind of see how that linear relationship starts to form right before us. It is linear, and where does it cross the y-axis? Well, it crosses the y-axis at 0 and 6. So it doesn't go through the origin. It actually touches a little bit higher up. If we were to write an equation, what would it look like? Well, the cost is equal to $2 per topping plus a base cost of $6. How much would it cost if you were to get a pizza with 8 toppings? Well, we have our equation. We plug in the value that we're given, which is 8 toppings, and then we go ahead and solve for the whole cost. 2 times 8 is 16 plus 6 gives us 22, so it would be $22 for a pizza with 8 toppings. So that was an example of partial variation. So another way to say it, the cost of the pizza varies partially with the number of toppings. It isn't directly related, it is partially related. So if it varies partially with the equation in the form y equals mx plus b, which looks very similar to what we just did here, y equals mx plus b, rate of change, rate of change is the 2, x is the independent variable, where x and y are constants. In this equation, b represents or equals the y-intercept, or where the line touches the y-axis. And the m represents the slope, or the constant variation, or the constant rate of change. The graph of a partially variation is a straight line that doesn't pass through the origin. And here are some examples here. This is partial variation, because they do not pass through the origin of the Cartesian plane. Last example here, copy and complete the table of values that y varies partially with x. So when x is 0, our y value is 4. When x is 1, our y value is 7. X is 2, y is 10, and so on and so forth. And if I go ahead and graph this, so x is 0, y is 4. X is 1, y is 7. X is 2, y is 10. And we see how that's kind of forming a line. Obviously not the best drawing line, but it's forming a line, and it touches the y-axis at the point 0 and 4. So what is the value of y, or the y-intercept, is 4. So the b value is 4. What is the constant of variation? Well, the difference between the y values. The difference between 7 and 4 is 3. The difference between 10 and 7 is 3. The difference between 13 and 10 is also 3. So the constant of variation, or the slope, is 3. So write an equation in the form of y equals mx plus b. Well, y is equal to our rate of change, which is 3x, plus our y-intercept, which is 4.